In multiple linear regression, Y squiggle dot means fit the saturated model. Use every other variable in the data. I'm going to do that with both data sets. If you look at the summaries, you can see that just transforming the variables raised the adjusted R squared a little from 0.779 to 0.7958. Now, looking at the pairs plot of the data I'm going to use, if I look at log displacement versus log horsepower, this one here, I see that they're pretty strongly correlated. That's multicollinearity. I might not want both variables in the model. Weight is correlated with both of these. So there's weight with log displacement, and here's weight with log horsepower. And weight is also correlated with drat. So we've got some multicollinearity, and if we were going for simplicity in the model, we might want to throw some of these out before we even begin the backward elimination process. First, let me get rid of those ordered categorical variables. I can't use this dot notation anymore, so the syntax is response squiggle and then each explanatory variable plus the others. If I look at the residual plots of residuals versus fitted, it doesn't look great. There's a slight V pattern, and that suggests the linearity assumption might be violated. I looked at one without the log transformation, and it actually looked worse, but it's not that bad, and there's not a lot of data here. If I saw 1 point here and then 1 point down here, it would be just about perfect. So I think I'm fine with this. If we're using the p-value approach, the t-tests rely on the normality assumption. In this case, the residuals don't look normal. There's definitely some right skew. Let's look at the QQ plot. That's not good. But the sample size is large enough that we can rely on the central limit theorem to make the t-tests valid. I'm going to ignore the multicollinearity and just fit the model using the backward elimination process. I'm starting with this one here, and I can see that VS has the highest p-value. So let's fit a model without that one. Drop VS. In this model, the highest p-value is drat, so fit a model without drat. Now, log displacement has the highest p-value, which is a surprise since it seemed to have a strong relationship with MPG. But in the presence of log horsepower and all these other variables, it appears to not be significant. And things might change if I dropped qsec instead, which has a pretty close p-value. There's barely any difference between them, but I'm going to stick with dropping the highest, which is log displacement. Now I drop qsec. Now I drop AM because 0.15397 is still higher than 0.05. Everything in the model is now significant. The final model I get through the backward elimination process is 59.57 minus 5.92 times log horsepower minus 3.29 times weight. When I dropped AM, the adjusted R squared went down slightly. The best model according to adjusted R squared was model 6. If we look at the residual plots, there's still that slight pattern in them, which isn't ideal. That's for 7 and for 6. There are various models you can come up with. If you're going for the most simple explanation for miles per gallon, you might stick with model 7. Or you might prefer model 6 because it has the highest adjusted R squared, which means the highest predictive power, though there's not much difference between the two. Finally, here's how to use these. If you're given the following information about a car, 200 horsepower, manual transmission, and it weighs 3.2 thousand pounds, the units for weight are thousands of pounds, then for model 6, it is 59 minus 6.49 times the log of 200. Remember, I have to take the log of horsepower, minus 2.47 times 3.2 plus 1.76 times 1 because it's a car with manual transmission. And that is 18.47. And according to model 7, it's 17.68. You see they're slightly different predictions.